All right, thank you so much. Yeah, so let's carry on. We have a few more minutes before our break, but that should be enough to define, introduce the definition of a coset space. So, the cosets of a group, under, say, a subgroup H, themselves form a set known as a coset space. And usually it's written by G over H. And so G over H is G up to the equivalence class, and it consists of, say, H, say G1H, G2H, dot, 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 GK minus 1H. Okay? So the elements of the coset themselves are sets. Sorry, the elements of the coset space themselves are sets, which are cosets. Okay? Is it clear what I mean by coset space?
Could you explain it a bit?
So yeah, like when we went over to the, let's go to the picture. So this was one coset, H. H is kind of the coset for, kind of the trivial one, but this is, say, another coset which was BH. And then there will be another coset, say, CH. So essentially what will happen is that this group will get divided into different cosets, right? So all of these domains are different cosets. So now if I take each of these cosets, treat them as an element for another set, that set is the coset space.
Okay, so, got it.
Okay. So in general, a coset space is not a group. But under some circumstances, we shall see when it is a group. Okay, so let's define a normal subgroup. We'll take a break after that. So, if all the left cosets are equal to the right cosets, then H is a normal subgroup. Okay, so G, that means if G of H is equals to H of G. So that means that if G of H1 is say H2 of G, right? If this is true, then we say H is a, so this is the H is a normal subgroup, okay? Another way of writing this is that G, a bit of an abuse of notation is this, okay? So this means that G of H1, G inverse gives you. Okay, so let's take a break now and we shall meet back here at 6:10, okay? Okay, so let's start. So let's make a few comments on normal subgroup and coset space. Okay, can you guys hear me?
Yes, sir.
Okay, so if H is a normal subgroup, then G over H, the coset space, is a group. Okay. And how does this work? So if, for example, say G1 and say G1 prime are in the same coset, that means that we can write G1 as G1 prime H. Okay, let's call it H1. And suppose that G2 is equivalent to G2 prime, that they're in the same coset, then G2 is equal to G2 prime of H2. They don't have to be in the same coset. Okay, so, and then let's look at the multiplication of G1 and G2. So according to these assumptions, we can write G1 as G1 prime H1, G2 as G2 prime H2, right? But we see that it's H is a normal subgroup. Okay, so if H is a normal subgroup, that means that what does this mean? This means that H1 G2 prime is going to be G2, say H1 prime, right? Or actually the other way around, sorry. If that means that it's going to be H1, say G2 prime, hang on, what do I?
So both are equivalent, I think. I mean, both approaches.
Yeah, exactly. Yeah. So exactly. So right. Thanks, Nahi. So the idea is that if I have something like, say, G, H1, G inverse as, say, H1 prime, then I can write this as, say, G, H1 equals to H1 prime G, right? So what this means is that I can write this thing as G1 prime. So this has this form, right? I can write this as, say, G2 prime and H1 prime H2. Okay, so let me just carry this on the side. Okay, so what this means is that we have G1 prime, G2 prime times some H, let's call it 3, H3, right? So that means that if G1 is in the coset as G1 prime and G2 is in the coset as G2 prime, then G1 times G2 is in the same coset as G1 prime, G2 prime. Okay, so essentially, that's the closure property. So using this, you can show that G over H, if H is a normal subgroup, is the coset space is a group. Okay. I'll actually give you a more detailed exercise below on this. So just hang on. So the next comment is that the coset space when it's a group, when it can be given a group structure like above, there could be other accidental group structures we don't care about. Is called, it has many names, but I think physicists usually call it a quotient group. Quotient group. Okay, so it's a G by H, and we say that G by H is extended to G by H. Okay, just jargon. Number 3 is that if G is abelian, then every subgroup H is normal, right? Because G, H, G inverse, because it's abelian, is H. Okay, so the exercise I want to give you, this is more well thought out, is the following. Say if G1H and G2H are two cosets, and H is a normal subgroup of G, then we can define a binary operation between the cosets as, say, G1H composed with G2H is equal to the coset of G1, G2H. Okay? And your exercise will be to show that with this definition, this definition as the group multiplication. G over H is a group. Okay. So essentially, just formalizing what I've said here. You just do that for the. But you're just basically given the definition, and you just have to satisfy that all the group axioms, all the group postulates are satisfied. Okay. I will give you a hint. H is the identity. Okay. All right. Any questions?
Sir, what does abelian mean? Point number 3.
Abelian. Oh, abelian means that if all the elements of a group commute, then that's an abelian group.
Okay.
So, of course, if it's commuting, then this means the left-hand side is simply G inverse H, and G inverse is E of H, right? So if a group is abelian, if all the elements commute, which is not the case for groups in general, then any subgroup it may have is a normal subgroup, right? So for example, we saw that all the real numbers under addition form a group, right? And it's an abelian group. So a subgroup of that are the integers. So that's an example of a normal subgroup, okay?
So I have a
question?
question.
Yeah.
I didn't exactly get the definition of a normal subgroup.
Yeah, so okay, let's go over that. Suppose that H is a subgroup of G, okay? Now, if you take some G and multiply it with H, and then you get, okay, so if you have this, so G inverse gives you, say, H prime, then H is a normal subgroup.
Oh, so
Okay,
if it gives an element of H.
Yeah,
Okay.
so, so we can write this as G of H as H inverse G, right?
Yeah.
So that means that if I have, so it's for all G. This has to be true for all G. So that means that, and for all H for all G. So that means that, this equation can be written as this for all G. So in other words, if the left cosets are equal to the right cosets, then the subgroup that you're using to construct those cosets is a normal subgroup.
So each left coset only is equal to its corresponding right coset, right?
Yeah, only if it's a normal subgroup.
Okay.
Otherwise, it's not.
So would you please explain this with an image or a diagram?
Yeah, I mean, there are even like examples that I will give you at some point, but the idea is that, so you have a group and you have a subgroup, And suppose that you have some G here, and you have E, you have H, blah, blah, and you left multiply by this G. And as you left multiply by G, you know, you create this set. Okay, this set is GH. Okay, but as you right multiply, what will happen is that, you know, if you right multiply E by G, you'll get the same element. But the other elements, you might get other things. Okay. So this is the set you get, subset you get by right multiplying G. Sorry, they should be of the same size, but you know, because yeah, anyway. Okay, so the idea is that these two sets need not be the same. However, if they are the same, then means that you know, it's a normal subgroup. Now, when they're same, does not mean that, you know, element by element this has to be true. This doesn't have to be true element by element. You know, it can be that when you left multiply G, H by G, and you right multiply H prime by G, you get the same element, so that you end up with the same set. But the idea is that at the end of the day, you know, these operations give you the same set. If that is the case, then we say H is normal. Okay.
Yes, sir, got it.
Okay. Saif?
Sir,
Yeah, makes sense.
Yeah, Shujosh?
sir, so H1 and H prime can be different, or do that?
Yes, yeah,
Okay.
it can be different, but the
Okay.
set, the two sets are the same. So, you know, G can act on E will give you G, but G acting on H from the left gives you, I'm sorry, suppose G acting on the left gives you this guy. So
Okay,
it
got
gives
it.
you this guy, okay? But G acting on the right of H gives you this guy. But in such a way that, you know, you get all these elements, but, you know, both of them are confined to the same set, okay? They don't go outside this set, okay?
So the right and left multiplication don't have to be the same element of H, and any element of H would give the same set of HG and GH.
Yes, or you can, yeah, exactly.
Then the small h, where the small h belongs, the capital H, that is a normal subgroup.
Yes, it's a normal subgroup. If it's a normal subgroup, then you get a quotient space, a quotient group. It's a consequence. I mean, one thing comes first. Okay, so shall we carry on? Okay, so I want to give you a
quotient group. Quotient.
So yeah, then it's a quotient group. If H is a normal subgroup, then under this multiplication, it's a quotient group.
Okay, got it.